Okay, well, thanks very much for inviting me. I might have taken the title of the conference too literally. But so, right, my topic is unlikely intersections involving polynomial orbits. So the basic definition, the basic object I'll talk about is if you have a field, you have a polynomial over the field, and you have an element of the field, the orbit of the element under the polynomial is just the collection of points you get to starting with that element and repeatedly applying the polynomial. So this is the same thing as the set of values of the iterates of the polynomial at this point. So fn of x is the nth iterate. And the basic questions I'll talk about are how big can be the intersection between two polynomial orbits? So orbits of two polynomials, orbits of points under two different polynomials, and how big can be the intersection between the orbit of one orbit and a subfield? Okay, so how many points in an orbit can be in a subfield? And actually, I should have said earlier that when I came here, I found out that almost everyone is in additive combinatorics. So, well, I'm not. But I thought maybe I would put some things on the right so that you can look at these if you get bored with what I'm talking about. And these might be differently interesting. So just so they're there. So the topic is unlikely intersection. So first we have to know what likely is. So the question is, what do we expect? And so we can make a heuristic if we just, so this is easier, the heuristic is easier for the intersection of orbits. If you just think, if I have two polynomials of fixed degrees, say degrees 5 and 7, then the number of coefficients you have there is, well, 6 for one of them and 8 for the other. So you have 14 free things to play around with, plus the C and the D. So you have 16. But it's really 2 less than that because you can conjugate everything by a degree 1 polynomial. So you really have degree plus 2 free things to play with. And each condition you impose, if you say that you want f11 of C to equal g14 of D, if you expand this horrible thing out, it's a polynomial equation in all of these unknowns. So each spot that you say this orbit should meet this orbit is one more polynomial constraint on the coefficients and the C and the D. And so it should happen that as soon as you have more constraints than parameters, you don't expect to find any solutions. So that says that the size of the intersection should be at most degree plus 2. I mean, of course this is false, because you could have f equals g. I mean, you could have c equals d. But, well, heuristics have some kind of assumption that the world is random behind them, and in that case, the world was not random. But still, I think this should be true when it's not false. I mean, it seems reasonable. This one, it's harder to make a heuristic for this one, the second one, but plus 2? Oh, it's because of the C and the D. Well, there's actually a 2 plus 2 minus 2. So a degree n polynomial has n plus 1 coefficients because it has a constant term. And also there's the C and the D, but then you lose 2 because of conjugating by the linear. It's harder to make a heuristic for the second problem. The way I did this was I turned the second problem into the first problem. So and this is an argument that I'll use a lot, so if L isn't K, then just Then I want to say that there's some, I might assume things are not purely inseparable. I come from a world where purely inseparable things are always assumed away. For the second problem, if L doesn't equal K, then just pick an embedding of L into its algebraic closure. So some homomorphism which fixes K, but does not fix L. Okay, so for instance, if L over K is Galois, just take any element of the Galois group that's not the identity element. And so once you've done this, then you conjugate F by sigma. So then the points in the orbit who are fixed by sigma are also in the orbit of right. So, yeah, this contains right, where F sigma is just the polynomial gotten by applying sigma to all the coefficients of F. And this is because applying sigma to the coefficients of F is really you're really conjugating in the polynomial ring. You're really conjugating by sigma, by the extension of sigma to the polynomial ring. So conjugation behaves very well under composition, and that's why, well, this thing is true. So basically the intersection with the subfield problem is more constrained than the intersection of two different polynomial orbits problem. So this is the trick that lets us get from the second question to the first, although we can go even further, because there are many sigmas and, well, there are more constraints. Oh. Okay, so so the first question, the most unlikely thing is that the intersection is infinite. And so that we can completely describe. So this is when the intersection is infinite. So for the first problem, this is a theorem with Dragos Gioka and Tom Tucker. If two complex polynomials that don't have degree 1 have orbits with infinite intersection, then they must have a common iterate. Okay, and this is what you would naively guess, because the converse is obvious. If you have a common iterate, then the orbit of any point under this common iterate is contained in this intersection. So just find some point with an infinite orbit, and then you're done. But this part is not so obvious, and I should maybe say that Ritt, in 1920, Ritt determined all polynomials with a common iterate. So polynomials with a common iterate are basically iterates of the same polynomial. Basically, if you have any polynomial, if you take its fifth iterate and its seventh, well, they have a common iterate with each other. There's one little issue which you can see from the example of x cubed and negative x cubed. X cubed and negative x cubed are not both iterates of one polynomial, but they have the same second iterate. And so there is this issue that if you have, the general statement is things should be simultaneously conjugate to the composition of iterates of one polynomial with a linear which semi-commutes with all theirs. But morally, the main case is that f and g are both iterates of the same polynomial. And so there were two really different papers. The first paper dealt with the case that the degrees have a common power. And that kind of used different methods than the second paper to deal with the case that the degrees do not have a common power. But anyway, there's a completely clean statement. We know exactly all polynomials. We need to rule out degree 1 because of examples like x plus 1. Like the orbit of 1 under x plus 1 is just 1, 2, 3, 4, 5. It's all positive integers. And that has infinite intersection with all kinds of things. You know, you take the orbit of 3 under x cubed plus 5x, and that's some random looking thing, but it has infinite intersection with the orbit of 1 under x plus 1. So it's just polynomials x plus a constant that mess things up in degree 1. Okay, so the second theorem, which is much more recent, the second theorem is from this year. So, I mean, it was proved this year, so it's far from published. But so this says if you have an extension, if you have a field extension where both fields have characteristic 0, and if you have a polynomial in the big field and an element of the big field so that the orbit contains infinitely many points in the small field, then some iterate of the polynomial must be in the small field. Okay, which again is what you would expect because the converse is obvious. If you have an iterate in the small field and one point in your orbit is in the small field, then the orbit of that point under this iterate is completely contained in the small field. So as long as it's infinite, I mean, so you're set. So that says that as long as the orbit of f under c itself is infinite and contains one point in the small field, if there's some iterate in the small field, then the intersection is infinite. So there's some version of the converse. And again, I was able to determine all polynomials which have an iterate in the subfield. And morally, they're kind of silly. Morally, they're just polynomials over the small field. Except they're polynomials over the small field, except then composed with a linear, where the linear polynomial is over the big field. And so then you can work out exactly the constraints on the linear and the shape of the polynomial that allows this to happen. Okay, so there's a complete description of when these intersections are infinite. Okay, so now I want to assume away all of the situations in theorems 1 and 2. And the question is, if the intersection is finite, then how big can it be? Sort of getting results, hopefully getting towards these heuristics. And so this started with a question Igor asked, I don't know, like not very long ago, 3 months ago at most, maybe 2 months ago. But he was asking, how bad is the dependence on the parameters? Like, are there some parameters that you get a uniform bound as you vary that parameter in the question? And I was very happy he asked, because it made me, I mean, in dealing with this question, I had to come up with a new and kind of better proof of theorem 1, which I'll sketch today. So the result I can prove is that if you have two polynomials, again of degree, maybe I should have said, note that in theorem 2 I didn't need to worry about degree 1. It's only theorem 1 that I need to worry about degree 1. So, okay. So in theorem 3 I have two polynomials of degree at least 2, and I have points where the orbits have a finite intersection. Then the size of the intersection can be bounded by a constant where the constant only depends on the polynomials and does not depend on the choice of C and D. And this constant also is explicitly computable. I mean, if you give me two f and g's, I can give you an algorithm which in finite time will actually give you this constant. And if we believe the Bombieri-Lang conjecture, which, I don't know, I think it might be over 50% of experts believe it now, then you can do much better. Then the constant should only depend on the degrees of f and g. And you can get that it depends on the degrees of f and g and the degree of the field extension you get by adjoining all coefficients of f and g to k, as long as this degree is finite. When you can probably do something when the degree is infinite, but I haven't worked that out yet. Okay, so there's some amount of uniformity, but I mean, there's still some ways to go. But this, what? This constant, what? Yeah. So I tell you what it is. The constant is, it's the sum of the numbers of points defined over k on finitely many explicit curves over k, where every curve has genus more than one. So no, but the proof of the Mordell conjecture shows you how to give an explicit bound on this. So if you're handed a curve of genus more than one, there is an algorithm to actually give an explicit bound on it. But it's not something like I can't give you any idea of the shape of this bound beforehand. It's just okay. And so theorem 4 is that there are exactly similar results for the size of the intersection of an orbit with a subfield when you have a field extension of characteristic zero fields. Right, so it's something bounded by just a constant depending on f. And if Bombieri-Lang holds, then you get the constant only depends on the degree of f and the degree of the extension gotten by adjoining the coefficients of f to k. Okay, so the proof. So how do we prove all these things? So the key, well, this is the geometric fact that I really prove that implies all the other things. Although then there's a lot more stuff that goes into proving this. But so wait, 9:15, 9:35. Oh, I have 15 minutes. Great. Okay. So the crucial point is that if you start with any integers bigger than 1, I can give you some explicit integer, and this one I really, with a little more work, I can give you a formula for it. I just haven't had time to work out exactly what it is. But there's some explicit integers so that if you give me any complex polynomials of those degrees m and n, then either they have a common iterate, or every irreducible factor of, if you take the nth iterate of f minus the nth iterate of g, of fn of x minus gn of y, every irreducible complex factor defines a curve of genus at least 2. Or you get two very special cases where f and g are basically x to the m and x to the n, or Chebyshev m and plus or minus Chebyshev n. So the Chebyshev polynomials, these are the things that take cosine theta to cosine n theta. So this is the real result. This is the thing that makes everything else work. So the reason is once you have genus at least 2, you can apply the Mordell conjecture. So Falting's theorem to say that if this thing was defined, well, for instance, if f and g are defined over a number field, then you know if you have a curve of genus at least 2, it has only finitely many points, and you can bound it. But you don't even need that. Falting's extended Falting's theorem to any finitely generated extension of Q. So it might be a transcendental extension. And the generalization's not hard. You just find the right values to plug in for all the transcendental generators in order to reduce the big question to the number field case. But the nice thing is f and g only have finitely many coefficients. So the field generated by their coefficients is a finitely generated extension of Q. So the Mordell conjecture holds for that field. So we automatically know that when you have genus at least 2, fn of x equals gn of y only has finitely many solutions, with x and y being in the field generated by the coefficients. Yeah. This has nothing to do with orbits. Yeah. Yeah. Well, the point is that this is almost always happening. No, let me explain it. So the way you should think of this is what really happens is that for almost any polynomials, you just take, this happens with n equals 1. For almost any polynomials, f of x minus g of y is irreducible of some big genus. And then any factor of this is going to, any factor of this gives you a curve that maps to that thing of big genus, so it has even bigger genus. Okay? Oh, I didn't think of how I'm going backwards. I'm tempted to just go up. Is that too insane? Yeah, it's too insane. Oh, that's already fine. Okay. Good. Okay, so let me explain how. I mean, theorem 5. This is hard. Like theorem 5. Theorem 5 depends on the classification of finite simple groups in kind of an absolutely crucial way. I don't think it's possible at this moment to prove theorem 5 without it. I mean, I don't think the technology in math exists to prove it without it. And really kind of in an ugly way. Like we needed to know all simple groups that have a factorization as a cyclic group times another group. And not a direct product or semi-direct product, just a set theoretic product. So simple group is set theoretic product of two subgroups, one is cyclic. And that's what we needed to know. And I can't fathom a way to get on top of that question without using the classification of finite simple groups. These are more elementary. I mean, these only depend on the Mordell conjecture, which is still hard, but not nearly like the classification of finite simple groups. Okay, so let me show you how do you get from theorem 5 to theorem 3. So. Actually, I'll get to theorem 3 and theorem 1. So how do you connect these things? Well, the key idea is that how do you turn the intersection of orbits into something at a finite level? Well, so the key point is that if you have fr of c is equal to gs of c, and r and s are at least n, sorry, then fn of fr minus n of c equals gn of so, I mean, this is a simple statement, but this is absolutely crucial because this says that if the intersection of the orbits is big, then we're getting lots and lots of solutions to fn of something equals gn of something. And these solutions all live in the ring generated by C and this should be D. C, D, and the coefficients of f and g. So they're living in some finitely generated field. And then we're going to use the Mordell conjecture. So, and there's another point I should say, that it's not a restriction to say that both of them are big, because the FR of C's are never going to repeat themselves. If they repeat themselves once, then they'll keep repeating themselves. It'll be pre-periodic and the orbit is finite, and you can control things separately using different methods. You can control those. So we get to assume that the orbit is infinite, so that there are only at most 2n solutions to this that have r less than or equal to n or s less than or equal to n. So most solutions will have both r and s big rather than just one of them being big. Well, actually, let me prove theorem 1 first, because it'll be easier. So if the intersection is infinite, then this equation has infinitely many solutions, with x and y being in the field generated by C, D, and the coefficients of f and g. But this is a finitely generated, these are finitely many numbers that are generating it. So this is a finitely generated field of characteristic 0. And then by Falting's generalization of Falting's theorem, I mean, this is something, this factor, if you split this up into components, you get finitely many components, and Falting's generalization of Falting's theorem says that one of them must be a curve of genus 0 or 1. Because you have a finitely generated field in which some curve has infinitely many points, and then that curve must have genus 0 or 1. This has to have an irreducible factor giving you a curve of genus 0 or 1. And now we apply theorem 5. So that says that case 2 of theorem 5 does not happen. And then we could have case 1, which is what we want, or we could have these cases 3 and 4. And in cases 3 and 4, I mean, those are just x to the n and x to the m, Chebyshev and Chebyshev. So those are really under control. And cases 3 and 4, we use different sort of number theoretic methods, class groups and unit groups to control those. But basically a little bit more work to deal with cases 3 and 4, and we have a new proof of theorem 1. And this same proof actually proves theorem 3 because the n from theorem 5 just depends on the degrees. So we start with that n. That says this fn of x minus gn of y, like we know the degrees of this thing. We know exactly how many irreducible factors it can have, and we can bound their genus only in terms of the degrees of the two polynomials. And then, well, that proves everything thanks to these heavy hammers, thanks to Mordell's conjecture. It proves the first part of theorem 3, and then thanks to the work of Caporazzo, Harris, and Mazur, with Bombieri-Lang, it gives you this better thing. So this is the crucial bit to get from get from theorem 5 to the other things. so I should say a little bit about proving Theorem 5. It's hard to get started on that. Theorem 5 was extremely difficult. This will be the, I mean, it's the combined result of a series of papers, but there's a lot that went into it. And as I said, we absolutely crucially used the classification of finite simple groups. Yeah, let me not go into that at this moment. I did want to mention these other things. So Theorem 7 was kind of an earlier and much easier version of, well, yeah, kind of Theorem 5. But the statement was quite a surprise to us, that if you have any polynomial with rational coefficients, then the function it gives you from Q to Q is at most 6 to 1, except for finitely many points. And we have similar results over any number field. And Theorem 8 is Theorem 8 Theorem 8 has many, let's see. Let me just say, Theorem 8 is the real work that goes into proving Theorem 5. So this was with one postdoc and one grad student, 7 undergrads, and me. And the reason I mentioned Theorem 8 here is that I think Theorem 8 should have lots of applications. And I'm hoping that it might have applications in additive combinatorics. I mean, the crucial thing is, so what it's saying is that we know all polynomials whose images intersect infinitely often. Okay, so if you have 2 rational polynomials, we can describe exactly when their images have infinite intersection. And we can give a much more precise version of this, but it's much longer also. But I mean, the nice thing is that it's known, and if you ever see an equation like this come up where you have some polynomial in M that might be coming from some family of polynomials is equal to some polynomial in N, and you get infinitely many solutions when you plug in rationals for M and N, then we really know this. So there was a previous similar result by Boulou and Tiki when you replace Q by Z. So when the images of the integers under 2 polynomials have infinite intersection. And that has been applied tons and tons of places. But completely different technology had to be invented to do the rational case. I feel like there was something, there was one more thing I was supposed to say. There was another there was one more huge tool. Maybe. Okay, let me just tell you one more big tool that was used. So to prove Theorem 5, we used this is really coming from a similar geometric theorem after we used Falting's theorem. This is really saying that these are really the cases where f of x minus g of y has an irreducible factor giving you a curve of genus 0 or 1. So this is really a geometric thing, just written after the application of Falting's rather than before. But another key tool, and this will be the final thing that I'll say, is that iterates of a complex polynomial do not have many different ways to decompose. Except for 2 special cases. So f could be conjugate bilinear to either x to the n or plus or minus Chebyshev. And then its iterates decompose in all crazy kinds of ways. Like x to the 6th, if you took its 100th iterate, You get x to the 6 to the 100th. Well, that's x to the 2 to the 100th composed with x to the 3 to the 100th. So there are lots and lots of ways for iterates of x to the n to decompose. But the result is that for all other polynomials, their big numbered iterates can't decompose any differently than the small numbered iterates. The only difference is just by sticking copies of the polynomial on the outside. So if f m of x is equal to some composition of two polynomials, then you can pull off copies of f from the outside. So there's fr, there's the real g, and there's some nothing. And the real h, and then some other stuff from the outside. Where the stuff on the inside, I mean, so of course you can put you can put copies of f on the outside without affecting anything. The inside stuff, the crucial stuff, is a low numbered iterate. So t is at most log base 2 of the degree. So what this is saying is once you found all decompositions of the log 2 of nth numbered iterate of f, you've also found all decompositions of all iterates. And this was a surprising thing. This is joint with Peter Mueller. But at a crucial point, we absolutely needed this in order to, well, basically in order to deal with this irritating common factor of h that shows up on the left. We could throw that away because of, we proved this result in order to throw that away, actually. Okay, well, thank you very much for your attention. My methods can't see that, I don't think. Wait, let me think about this. I don't think the methods that I've shown touch that question.
Yeah, this method give nothing.
No,
Part 3, you've got the upper bound of 28. I mean, have you got examples where
yes.
Big degree polynomials occur?
Yeah, 28 cannot be improved, and we actually have an explicit list of all examples of degree up to 28. I mean.
Wow.
And I can even say more. If in these cases, like if it's x to the n, we explicitly know the other one. If it's Chebyshev, the other one is a solution of some polynomial Pell equation, and we can say a lot about the solutions. But well, over Q we can actually. No, there's one case where it's. If we assume some conjectures, we can just explicitly describe everything over Q.